I would love to do it on. The question was, when are we gonna have our math test? I don't want to do it too soon, so I'm thinking about like April 13th. Yeah. Excuse me. Sorry about that. So yeah, so I'm thinking about April 13th for our next exam. I'm a, I got you. I'm gonna make an announcement with all of the topics there and the videos and all that. All you have to do between now and then is finish your homework. That's not too bad, right? Yeah. To my knowledge, no. There's tutoring today, there's tutoring tomorrow, and then not after that, no more. And then next week, Saturday, there'll be tutoring. I could be wrong about that. There might be tutoring next week, Friday also. I think it's next week, Friday. There'll be in-person and online tutoring, and Saturday in-person online tutoring, and then everything is back to normal, April 13, Monday, April 13. Yeah. Mm. Yeah. I yeah, I'll do it today. Yeah. It'll be late though. I gotta go work after this. So yeah. So other than that, any questions anybody has? Anything from the homework? Everything has been posted. All right. You finished everything?
This month,
All right.
quiz.
All right.
Here's my quiz.
If you got everything, then we
Yeah. So this is so I made it. I did it back again. So this
okay.
one, mean, median, mode, standard deviations. Now it's slower.
Okay.
It's good, yeah.
And you got the range on there too?
Oh, the range, but you don't have any.
I don't have range there? Yeah.
Okay, I can do it now. The
Okay.
range is easy. And here I do have it, the range, the
Okay.
simple standard deviation, the coefficient variation, and the
Okay.
mode is right here, mean, mode, and median.
Okay.
You see, now let me do it.
All right. All right. So no questions? Just want to jump into today's lecture? I mean, that's cool. Today gonna be real easy anyway. Sure. Yeah, so we got a real easy lecture today. Nothing crazy, nothing complicated. Got you. I appreciate it. All right. All right. You have class after this? I was gonna say if you came to tutoring, I would look at it and then give it back to you. Oh, appreciate it. All right. All right. So let's look at what we're getting into. We're gonna be talking about additional properties of the binomial distribution. This is cool, right? So graphing a binomial distribution, any probability distribution may be represented in graphic form. How should we graph the binomial distribution? Remember, the binomial distribution tells us the probability of our successes out of n trials. Hey, therefore, we'll place values of R along the horizontal axis and values of the probability of R on the vertical axis. The binomial distribution is a discrete probability distribution because R can assume any only whole number values such as 0, 1, 2, 3, etc., right? Therefore, a histogram is an appropriate graph of a binomial distribution. All right, let's keep talking about it. So we throwing it back a little bit, just a little bit. Remember earlier in the class when we talked about the histogram? So we're applying that to the binomial distribution now. So here's the sauce right here, all right? So how to graph the binomial distribution. Place R values on the horizontal axis. Place the probability of R values on the vertical axis. And then step three, construct a bar over each R value extending from R minus 0.5 to R plus 0.5, right? And then the height of the corresponding bar is the probability of R. Remember when we were doing histograms before, how we had the class width, excuse me, not the class width, class boundaries, I meant to say, right? So instead of having class boundaries here, you're just going to have the actual R value in the middle, right? And we're not going to really distinguish like where it's beginning and ending, just that this particular bar represents the number five, for example, right? I'm going to show you guys an example. So let's check this out. So this is an example. A waiter at the Green Spot restaurant has learned from long experience that the probability that a lone diner will leave a tip is only 0.7, right? During one lunch hour break, right? The waiter serves six people who are dining by themselves. Make a graph of the binomial probability distribution that shows the probabilities that 0, 1, 2, 3, 4, 5, or all six lone diners will leave a tip, right? So this is not too bad. We already know the answer to all these probabilities, right? Remember, we could find that in our table. Let me get the table open real quick. So just switching back to our formula sheet, right? We know that our sample size right here is six, right? So I'm just gonna go to six. So two, three, four, five, six right here, right? My probability of success that we set in the question was 0.7, right? So here goes the 0.70 right here, right? Going down that same row, we know that that's gonna be right here. And these are my numbers, right? So the probability of 0 is 0.001, probability of 1, 0.101, etc. Right? So what I could do, I'm just going to cut this out. Now we're going to go back over here. So I just want to know what are all my probabilities, right? So let's say I have my R, and then I have my P of R, right? So this is the 0, 1, 2, 3, 4, 5, and 6. And then this column are all my answers, right? So this is the 0.001, the 0.010, and the 0.060, 0.185, 0.324, 0.303, 0.118, right? And remember how we get those? You can use a formula to get them, blah, 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 or you can use a table, or you can use a calculator. Your choice. Yeah, no problem. Yeah. All right. So what do I want to do with all these numbers? As the question was asking, I want to graph them, right? So when I'm making a graph real quick, I just need to drop down just to draw this little part here, right? We're drawing a histogram. Remember, the first thing we want to do, we want to skip a few numbers. Let's skip a few numbers. And I want to start off at what? At 0, and then go over to 1, to 2, to 3, to 4. Hold on, I don't like that 4. Let me try that again. To 4, to 5, and to 6. These are my R's, right? My number of successes, right? The next thing I want to do is I want to look back at this column stuff here, right? What's the biggest number I got here? The biggest number is 0.324, right? 0.324. So I want to make sure that my y-axis incorporates up to 0.324, right? So I want to go from 0, and I'm just going to go up by 0.10. You can do whatever you want with this, right? So this is like 0.10. Wait, not 10. Yeah, 10. I'm right. Call this 0.20. Call this 0.30. Call the top 0.40. I'm just making it up, right? You guys have autonomy, make up the axis so however you see fit, whatever you guys want, no problem, right? Right. So this is the probability R. Mm-hmm. Right. Well, for zero, right? And it's 0.001. So 0.001 is real small. So it's gonna be something like this, right? Now you see how the R value is in the middle of the bar, right? I don't care about where it starts and ends, just right stab in the middle. The next one for one, I forgot, is 0.01. 0.01. So this is just a little bit bigger. Come up here, right? This is not really drawn to scale. I'm not an artist. I'm just trying over here. The next one is zero point 0.6. Zero point 0.6 is just a little bit bigger than that. You get the idea, right? The next one is 0.8185, whatever. So that's going to be somewhere up here. Again, just trying my best. Not expecting like the sun, the moon, the stars. Next one is 324. So that one is like way up here somewhere. Whatever. Next one is 303, which is going to be a little bit less than that. So let's say somewhere like here. And last one is 0.18, which I'm guessing is somewhere like here. Hold on. Maybe here is a better number. Something like that. And there you go. There goes your histogram. All right. Maybe you want to put a little distinguishing mark in between all of them. Like what I like to do, I like to write what I was intending to get. This is 0.118, 0.303, 0.324, and I forgot the rest, 0.185, 0.010. I think next one is 6. No. Oh Lord, why did that happen? Sorry about that, y'all. 185.060, 0.010, 0.001. So however you want to do it. You want to draw hearts in it, be my guess. Just something to distinguish each bar from one another, you know? And that's the whole histogram. Questions on this? I don't know why the two disappeared. Questions on this? Mm-hmm. You want to see the original question, this thing? Okay, there you go. And then that part that I wrote there, I'm literally just copying the table from your formula sheet. Like that's all on your formula sheet. Um, Everybody good? Mhm. Right. So you n find six. Then you're gonna go across the top to find the point 70, right? Because that's what they gave us. And then you go down to where that column is. Right? Mhm. That's what they gave us. The n is six in the question. Yeah. Yeah. Uh-huh. Right. Yeah. So N6 right here, and then point oh 0.07 up top, come down, and then this column, this is the one that you want. Yeah. Point 0.70. Yeah, that's the one. Yeah. And it's come down to where the six is, yeah. Yeah. That whole column coming straight down. Go ahead. Right. Like what they're asking is what's the likelihood of like one person giving a tip, two, three, four, individually, and that's what these numbers are. The individual chance that one or two of them will give a tip. Yeah. Well, it can't be seven because the n is six. Yeah, so the most could be six. Well, in this question, it's like that, but it's possible that there could be a seven. It depends on the question that's given. Yeah. Mhm. You're welcome. Just copy. Just copy. Yeah. Yeah. There's no calculations, just graph it. No, it's on the homework though. Yeah. So you would just do it the old way, the way we did last class, where you find each individual probability with the NPR. So N is six, the probability of success is 0.7, and then here's your R's. You find it for zero, find it for one, for two, for three, for four, for five, for six. Right. Yeah. Or the calculator. Use a calculator too. Yeah. So real quick, like I am trying my best, but I admit I'm not the best at art. This is what I was trying to draw. So y'all can see. This is the computer version of what I was trying to do. Yeah. So yeah. Mhm. Mhm. For homework you do. Yeah. Let's look at another example real quick. This is not too bad. So Jim enjoys playing basketball. He figures that he makes about 50% of the field goals that he attempts during a game. Make a histogram showing the probability that Jim will make 0, 1, 2, 3, 4, 5, 6 shots out of the six attempted field goals. This is a binomial experiment with n equals to six, right? Hey. So we know this is six because he's going to take a total of six shots during the basketball game, right? Anyway, in this situation, we'll say success occurs when Jim makes the free throw, the field goal, excuse me. So what is a probability of success? We know that's going to be 50 or P is equal to 0.5, right? Because I was given in the question. After that, you could look it up in the table, right? You all have the table. N is six. Probability of success is 0.5. You could get all these numbers here, right? For 0, 1, 2, 3, 4, 5, 6, right? Here goes the column of information. You could fill that out, right? All on your formula sheet, just copy and paste. Not really. No. But you should know how to look this up though. So if I ask you what's the probability of two, you should be able to go into the table and be like, okay, oh, it's just 0.234. And then that's the end of the question. Yeah. Like my test questions are a lot simpler than this. Like I'm not asking you something specific and you just look it up and give me the answer. That's all. Or type it in your calculator and give me the answer that way. I don't care. Mhm. Your choice, your choice. But the table is easier. And then same game as before. You can actually use this information to draw a histogram. It's drawn the same way, where the R's are in the middle of each bar. As you can see here, I don't feel like drawing another one, so I'm just going to show you, right? So this is like half of the graph that was given. They ask you to finish it, so this would be the whole graph, right? Notice that this graph in particular, right, is more symmetrical, right, than the previous graph that I drew. Right? Whatever's on the left hand side looks like it's on the right hand side. Like I could, it's wrong pen. I could literally like fold this in half, right? And whatever's on the left hand side matches what's on the right hand side, right? The reason for that is because of this. My probability of success is 0.5. That's like the perfect balancing point. That's why it looks so symmetric. The left side looks like the right side. I mean, mine was symmetric too, but it was a little skewed, like there was a little bit of a skew to the right, right? Because we were 0.7, but 0.5 is like perfect, right there in the middle. Mhm. Same thing. I could ask you what the probability of R is. Good stuff. All right. Mm-hmm. The probability of success is 0.7. Yeah, that's right. Right. Like when R is equal to one or R is equal to zero, it gives you a different probability. Yeah. I don't remember if I posted a update, like a announcement with the new material, but it is on YouTube, all the new material. Yeah. I do remember uploading something last night, so like but I didn't write a update about it, but I will get an update about it soon. My next update is gonna just be like it'll be this video too, but also like the topics for the exam, like what's gonna be on it. You guys can just practice that, do your homework, right? Y'all know I just copy the questions from the homework, right? That's all I'm doing. All right. So in example 6 and guided exercise 6, we see the graphs of two binomial distributions associated with n equals 6 trials. The two graphs are different because the probability of success P is different in two cases. In example 6, we had the probability of 0.7. So, all right, that's our probability of success. And the graph was skewed to the left. So that is a left tail is longer. In guided exercise 6, right, the probability is equal to 0.5, which is in the middle. And that graph is something that is more symmetric, right? So that is if we fold it in half, the two halves coincide exactly. So whenever the probability of success is equal to 0.5, the graph of a binomial distribution will be symmetric no matter how many trials we have, right? Later in chapter 7, we're going to see that if the number of trials n is quite large, the binomial distribution is almost symmetric over the bars containing most of the area, even when the probability is not close to 0.5. So law of large numbers, the larger the sample size, the more that the graph will look normal, right? That's the lesson there. So what does the graph of a binomial probability distribution tell us? Consider a binomial probability distribution with n trials and probability of success on a single trial p. The graph of the distribution tells us the probability of r successes for each r from 0 to n. If the graph is mound shaped and symmetric, the probability of success of p is close to 0.5. If the graph is skewed to the right, the probability of success p is less than 0.5. The more skewed to the right the graph, the closer p is to 0. If the graph is skewed to the left, though, the probability of success p is greater than 0.5, and the more skewed to the left the graph is, the closer p is to 1. All right. Questions about this? It's just the interpretation stuff right here. You will see a question like that on your test, on your homework, excuse me. Yep. And again, everything's been posted so y'all can take a look at it. Right. It's symmetric. It's perfect, symmetric. Yeah. So this is what I really want to get to. Let's get to the easy stuff now. This is on your test. So the mean and standard deviation of a binomial distribution. Two other features that help describe the graph of any distribution are the balance point of the distribution and the spread of the distribution about the balance point. The balance point is the mean mu of the distribution, and the measure of the spread that is most commonly used is a standard deviation sigma, right? The mean mu is the expected value. Remember that word, expected value, right? That's associated with the mean, right? So the mean mu is the expected value of the number of successes. For the binomial distribution, we can use two special formulas to compute the mean mu and the standard deviation sigma. These are easier to use than the general formulas that we talked about in last chapter. So let me show y'all them right now. This is going to be great. I'm going to give y'all the source. You guys have these formulas written down in your formula sheet, so you don't need to stress. So here you go. So how to compute the mean mu, the population mean, and the population standard deviation sigma for a binomial distribution. Mu is equal to n times p, right? Literally just take the n and multiply it times the probability of success. That's it. And that is the expected number of successes for the random variable r. Keyword there is expected, right? When you're seeing these word problems, they're going to ask you flat out, what is the expected value? What are they asking you? They ask you for the population mean, which is mu. Next, they're going to say, what is the standard deviation, sigma, right? So that's going to be equal to the square root of n times p times q. Right? Remember, p is your probability of success, q is your probability of failure, right? And that is the standard deviation for a random variable r, where r is a random variable representing the number of successes in a binomial distribution. N is the number of trials. P is the probability of success on a single trial. And Q is the probability of failure, which is equal to 1 minus P, right? That's the complement of success, right? Is failure. Okay. It says, let's compute the mean and standard deviation for the distribution of example 6 that describes the probability of lone diners leaving tips at the Green Spot restaurant. Just to recap, n is equal to 6, P is equal to 0.7. All right. They said they want the mean and they want the standard deviation. Right? Let's pretend that I didn't know what to do. So if I don't know what to do, like say I'm on the test, I don't know what to do, right? Go straight to your formula sheet. The answers for your entire test is on the formula sheet, right? Scroll down to chapter 6, right here, right? You see right here where it says mean? There you go. That's the formula. Mu equals n times p. Standard deviation, sigma is equal to the square root of n times p times q. If you forget what they are, here they are. This is R, number of successes. Hey, this is P, your probability of success. This is Q, right? Your probability of failure, right? N is all the way up here at the top. It's your sample size. So you're good to go. You have everything. All right. Let's cut this out. I think I could do a better job than that. Give me 1 second. And then let's go back. So here goes my formula right here. So mean is equal to mu, which is equal to n times p. So after that, literally just type it in your calculator. 6 times 0.7. What's the answer? That's what I'm talking about. All right, a little bit harder. Standard deviation is equal to sigma, which is equal to the square root of n times p times 1 minus p. All right? Just plug in the numbers. Nothing crazy. It's the square root 6 times 0.7 times 1 minus 0.7. Simple, simple work. What's the answer? Mhm.
1 minus 0.7.
Yeah, that's the answer, 4.122. Ain't that? 1.122. Okay. Everybody else got that answer? With the square root, yeah. Success, yeah. Mm-hmm. Because it's the complement of it. Yeah. And if you forget, it's right here, the formula sheet. So mu is our population mean, right? And sigma is our population standard deviation. Remember, anytime they ask you for something that's Greek, mu, sigma, theta, that kind of stuff, they're talking about, or rho, I should say, they're talking about a population parameter. But if they use a English term, X bar, S, R, those kinds of things, right? then that's going to be a sample, right? So instead of a sample statistic, right? Instead of a parameter. I got 1.35. 1.35. I'm not sure. All right, let's see. Let's see what I get. Does anybody need to see how to do this in the calculator? Or can I assume that y'all know how to do it? Y'all want to see? Okay. I was about to say I'm winning, not a single ad, and then here comes four ads. Yeah, yeah, it'd be like that. They wasting their time marketing on me because I'm not gonna buy nothing. Like, no, no. All right. So let's say I want to type this in the calculator, right? What am I gonna do? I'm gonna go second square root and just type what you see, right? So it's gonna be 6 times 0.7 times, now open parentheses, 1 minus 0.7. Close parentheses. Same procedure, same everything. And I got your answer, right? 1.1224. Okay. That's what I meant by the dot, by the way. That dot means multiplication. Like when I say 6 dot 0.7 dot, that meant multiplication. That's my fault though. That should have been an X though. I just felt like, hold on. Boy, why did that happen? I just felt like I didn't have enough space, so that's why I did that. 1 second. Sorry about that. Yeah, my fault. Yeah, I just felt like space was limited, so that's why I didn't do it. But yeah, that should have been an X there to indicate multiplication. Yeah. Any questions on this? It's on your test, and you have many questions like this on your homework. Enjoy. Mm. Oh, a lot, like six, for homework. For the test, you got like a single question. Yeah. Huh? It will be. Yeah. But all you got to do is copy, right? I didn't make up nothing here. I just copied. That's all I did. Yeah. Yeah. You'll be good. You got days to study it. A whole week. Yeah. I mean, the more the better, because then that's the less points that each question is worth. Yeah. Yeah. Nah, like um I'm gonna send out a message on this, but it's more like 4, 5, 6. Yeah. Like 13. Yeah, yeah, yeah. I figured I wanted to pick a really bad day, and what day is worse than a 13, right? Yeah. All right, so we good? No questions on this? All right. This should be like the hardest question on your test. Also, over the break, this would be a good time to get to know your calculators. Use the calculators while you're doing your homework. They help. All right. All right, bear with me 1 second. I'm about to throw it back to chapter two for a second. Just because we want to tie this all together, you know? It's all related. 1 sec. I don't know why this joint is not highlighting for me. There we go. Sorry about that. Okay. So I just want to make a quick note. So unusual values. So Chebyshev's theorem tells us that no matter what the data distribution looks like, at least 75% of the data will fall within two standard deviations of the mean. As we're going to see in the next chapter, when the distribution is mound-shaped and symmetric, about 95% of the data falls within two standard deviations of the mean. Excuse me. Data values beyond two standard deviations, right, from the mean are less common and than those closer to the mean. In fact, one indicator that a data value might be an outlier is that it is more than 2.5 standard deviations from the mean, right? Unusual value. So for a binomial distribution, it is unusual for the number of successes R to be higher than mu plus 2.5 sigma or lower than mu minus 2.5 sigma. If it is, then that's considered an outlier, right? So we could use this indicator to determine whether a specified number of successes out of n trials in a binomial experiment are unusual. For instance, consider a binomial experiment with 20 trials for which the probability of success on a single trial is p is equal to 0.70. The expected number of successes is mu is equal to 14 with a standard deviation of sigma is equal to 2. A number of successes above 19 or below 9 would be considered unusual. However, such numbers of successes are possible, right? So yeah, like an example that I could give you, I feel like I mentioned this before, but I don't know if you guys remember, right? That this class is like part of like a special set of classes, right? They call SI classes. That's why you guys have Jovine in the class, right? So when they examine the data for this class, they're going to look at everybody's grades and all that to see how did you guys do versus another class that didn't have Jovine, for example, right? They could look at you guys in totality, right? But that would actually be really dumb, in my opinion, right? Why would it be dumb? Because of this, right? These unusual values, right? There are some of you that are sitting in this class where no matter how great of a professor I am or how great Jovine is, you're still going to get an A. It didn't matter whether you were in the regular class or this class, you're still going to get an A, right? So why look at the data on you? That's not anything in great. That's an outlier, right? As well as there's some of you that no matter how good I am, no matter how good Jovine is, you're still gonna get an F, right? There's some people where they have outside issues that's gonna prevent them from succeeding in the course, all right? Those people are outliers. It's the middle portion of y'all that they really should be looking at, right? Those of you that, let's say, had you not been here, you were in the regular class, you would have gotten a C instead of a B. That's who y'all they need to study to see how they can make it better so that everybody could get B's instead of C's or D's. All right. So that's an example. That's a real world example of this topic that we're looking at. All right. Next thing, and this is already posted as well. I want to talk about the graphs of normal probability distributions. This is cool, right? So now we're crossing over into the next section. Oh man. Now I know most of you after this class, you're probably gonna want to consider changing your major to math, right? And then taking calculus and all that. All right. So we're gonna talk a little bit about that. Mhm. Huh? Math buildings? Yeah, yeah. I was a math major when I was here. Yeah, yeah. Just saying, like, if NYPD don't work out, be a math major. You know? All right. So, one of the most important examples of a continuous probability distribution is the normal distribution. This distribution was studied by a French mathematician, right, called de Morvay, and later by a German mathematician called Gauss, right, whose work is so important that the normal distribution is sometimes called Gaussian, right? The work of these mathematicians provided a foundation on which the theory of statistical inference is based, right? So I'm throwing it back to the beginning of the class, right? Remember, I told you guys we're gonna be looking at statistics, right? And and probability, but there's gonna be a third part of the class called statistical inference, right? The statistical inference is more of a real life scenario, right? The issue that I have is that for many reasons, maybe it costs too much money, maybe it's impossible. Like I'm interested to know what a population parameter is, but for whatever reason, I can't get that population parameter. I have to just settle for a statistic, right? An example I could give you guys. I don't know if y'all know about this, but they got this war going on in Iraq. Y'all heard about it? Heard? Was Iran? Dang, man. I messed up. I messed up. Yeah. But look, let's say that I wanted to know what the United States, whole country, feels about that war, right? Now, I can't really go physically go up to everybody and be like, yo, what you think? What you think? What you think? But what I could do is I could take a sample, and from that sample, I could make a inference, educated guess as to what the country feels, right? There's a lot of problems in what I just said, though. Go ahead. How do you feel about it? Me? It sucks. You know? Um, I don't know. Like it's a mixed feeling. On the one hand, I hear what they're saying about the oil and the oil prices and all that. On the other hand, like it really sucks. Like they tried to pull a Venezuela over there, but Venezuela is not. What was it? Iran or whatever. Yeah. So, but the long story short, right? I want to know what the parameters are. I want to know what the population mean is. I want to know what the population standard deviation is. I don't care what, let's say, the Bronx's feelings are, right? But the Bronx's feelings is all that I could possibly get to make that educated guess, right? So this topic that we're going into is the beginning, right, of our journey to making those educated guesses as to what the parameters would be. All right. So it's really, really cool. So the first thing I want to show y'all is the bell curve. I don't know if you guys ever seen this before. Right. So this is a bell curve, right? A normal distribution. Let's talk about it a little bit, right? So this is how it looks, right? There's no y-axis, right? There's an x-axis, as you guys can see, right? In the dead center, this is your population mean mu. That's your balancing point right there in the middle, right? If you go one standard deviation over to the right, so that's mu plus sigma, and you go one standard deviation over to the left, that's mu minus sigma, and you go up to the graph itself, right? This is what's called your inflection points, right? So inflection points is are where the curve kind of changes direction, you know? So let's jump into calculus for a second. In calculus, they have an idea called concavity, right? Think of concavity as like a cup, right? I'm not going to use that cup. Think of it as a cup, right? So this would be called concave up. You can hold liquid inside that cup. If you flip it upside down, this is called concave down, right? The inflection point is where the graph switches from being concave up to concave down or reverse concave up to I mean concave down to concave up, right? So that's what's happening here. This is the concave up. This is the part where you can hold the water. This is the concave down. This is the part where your cup is empty, right? And then right back to being concave up, right? Those are your inflection points, all right? If we were talking about slopes, right? You could say that the slope of this curve, right, is increasing, increasing, increasing. When it gets to the top, your slope is zero. And then over here is just decreasing, decreasing, decreasing. All right. Okay. Another last thing to mention about this, right? Over here, right? This curve keeps going on, right? This curve does not touch the x-axis. It will come very, very, very close to the x-axis, but it will not touch it. All right. That's another little tidbit of information about this. All right. In calculus, you'll learn why. Any questions about this so far? Both the end parts, those end parts right here, like over here and over here, it's gonna keep going really, it's gonna get really close to it, right? But it'll never actually touch it. All right. Just an idea that I want you guys to keep in your head. All right. And that's a normal distribution. Hmm. Um, yes, it is a standard. Why they call it normal, I have to research that. I don't remember why they call it normal, but that is a good question. It's a really good question. Something I forgot to mention, right? You could also go further out, right? This is two standard deviations away from the mean. This is mu plus two sigma. Two standard deviations away from the mean on the left-hand side. This is mu minus two sigma. You can also go three standard deviations away. It's mu plus three sigma. You can also go three standard deviations away on the left. Mu minus three sigma. All right. And that makes up the whole normal distribution curve. That's it. You know? This is a continuous distribution. Remember when we were doing binomial, everything was discrete. You could count distributions. This is not discrete. This is a continuous, right? So something I might ask you is, excuse me, I might ask you for the area under this curve, right? That's another calculus term. But just know that the area under the curve is equal to the probability, right? So I might say, oh, from right here, this shaded part right here, what's that area? Very simply, all you have to do is just look it up in the table, give me back the answer, and we're done. Or type it in the calculator, give me the answer, whatever you like better, right? And we're done. That's it. So this is a very easy section. You literally just copy, right? And that's it. So let's get more into it. This is gonna be dope. All right, so applications of the normal probability distribution are so numerous that some mathematicians refer to it as a veritable Boy Scout knife of statistics. However, before we can apply it, we must examine some of the properties of a normal distribution. A rather complicated formula presented later in this section defines a normal distribution in terms of the population mean mu and the population standard deviation sigma, the mean and standard deviation of population distribution. It is only through this formula that we can verify if a distribution is normal. However, we can look at the graph of a normal distribution and get a good pictorial idea of some of the essential features of any normal distribution, right? Which we just saw. So now let's describe this graph. Right? Another name for this is also the bell curve. All right. I guess different poets have different names for different things, whatever. All right. So the graph of a normal distribution is called a normal curve. It possesses a shape much like a cross section of a pile of dry sand. Because of its shape, blacksmiths would sometimes use a pile of dry sand in the construction of a mold for a bell, right? Thus, the normal curve is also called a bell-shaped curve, right? We see that a general normal curve is smooth and symmetric about the vertical line extending upward from the mean mu. Notice that the highest point on the curve occurs over mu, right? If the distribution were graphed on a piece of paper, right, or a piece of sheet metal, excuse me, cut out, and you place on a on a knife's edge, right? So you have like a sheet of paper, you place it on a knife's edge. The balance point would be at mu, the population mean. We also see that the curve tends to level out and approach the horizontal x-axis like a glider making a landing. However, in mathematical theory, such a glider would never quite finish its landing because the normal curve never touches the horizontal axis, right? The parameter sigma controls the spread of the curve. The curve is quite close to the horizontal axis, mu plus 3 sigma and mu minus 3 sigma. Thus, if the standard deviation sigma is large, the curve will be more spread out. If it is small, the curve will be more peaked, right? This next figure is going to show you a normal curve cupped downward for an interval, excuse me, sorry, on either side of the mean mu. Then it begins to cup upward as we go to the lower part of the bell. The exact place where the transition between the upward and downward cupping occurs above the points mu plus sigma and mu minus sigma. In terminologies of calculus, transition points such as these are called inflection points. All right. And you guys would laugh in calculus how easy it is to find an inflection point. It sounds complicated, but it's not. Mm. Again, all of this is posted so you guys can review. So let's talk about some important properties of a normal distribution. The curve is bell-shaped with the highest point over the mean mu. The curve is symmetric about a vertical line through mu. The curve approaches the horizontal axis but never touches or crosses it. The inflection transition points between the cupping upward and downward occur above mu plus sigma and mu minus sigma. The area under the entire curve is 1. The parameters that control the shape of a curve, of a normal curve, are the mean mu and the standard deviation sigma. When both the mean and standard deviation are specified, a specific normal curve is determined. In brief, mu locates the balance point and sigma determines the extent of the spread. right? How spread out it will be. Oh, baby, here it is. Here it is. Can't wait to show you all this. So the normal curve, right, is always above the horizontal axis. The area beneath the curve and above the axis is exactly one. As such, the normal distribution curve is an example of a density curve, right? You guys might have noticed that the new video that I posted was called cumulative density function, CDF, right? This is related to that. The formula used to generate the shape of the normal distribution curve is called the normal density function, right? If x is a normal random variable with mean, mu, and standard deviation sigma, the formula for the normal density function is this. F of x is equal to e raised to the negative half power times x minus mu over sigma squared divided by sigma times the square root of 2 pi. Cool. All right. So using calculus and this formula right here, that's how we actually make our normal distribution table, right? Which we're going to get to in a little bit. But if you guys look in your formula sheet, there's a table there called normal distribution, the Z table. This is the formula that they use to make the Z table. All right. The total area under any normal curve studied in the book will always be 1. The graph of the normal distribution is important because the portion of the area under the curve above the given interval represents the probability that a measurement will lie in that interval, right? In a previous section, we studied Chebyshev's theorem. This theorem gives us information about the smallest portion of data that lies within 2, 3, or k standard deviations of the mean. This result applies to any distribution. However, for a normal distribution, we can get much more precise results, which is given by the empirical rule. All right. So, empirical rule, that's what's on your homework. Let's take a look at that. And I'm not gonna lie to you, like this table that I'm about to show you right here is the answer to your homework. I'm just telling you straight up. You could copy it if you want. That way you don't gotta stress. Otherwise, you might have to watch a video again and see this table again. But this is literally the answer to your homework right here. All right. So let's go through it. So for a distribution that symmetric and bell-shaped, in particular for a normal distribution, right? Approximately 68% of the data values will lie within one standard deviation on each side of the mean. So if the mean is in the middle, you go one standard deviation to the right, one standard deviation to the left. That's going to cover 68% of your data, right? Approximately 95% of your data will lie within two standard deviations on each side of the mean. So you go two standard deviations to the left, two standard deviations to the right. 95% of your data is covered within that, right? Approximately 99.7% or almost all of your data values will lie within three standard deviations on each side of the mean, right? So you go three standard deviations to the right, three standard deviations to the left, whatever's in the middle, that's 99.97% of your data, right? So what are they going to ask you in your homework? For 99.7% of your data, how many standard deviations away are you? Three. Done, right? For one standard deviation from the mean, right, on the left and the right, how much data is covered in that? 68% done. You know, that's your whole homework right there. Y'all can take a picture if y'all want. It's only like three questions, but that's the answer for it. Mhm. Mhm. Sometimes it's not. really clear when you have words. So let me just show y'all what it looks like. So this is what I'm trying to describe to you right now, right? So right here, we're at the mean mu. If we go one standard deviation to the right, one standard deviation to the left, 68% of the data is going to be within that, right? So if you go, if you, let's say you just want to go from the mean to one standard deviation to the left, that's just 34% of the data, all right? Same thing with the 95, two to the left, two to the right, that's 95%. You just add up all these data points here and they add up to 95%. You go three to the left, three to the right, you just add up including the 2.35%, add them up, and then you get the 99.7. This is visually the answer to all the questions on your homework, right? Questions on that?
I'm
Good?
confused.
You confused?
Can ask you a question because I need to take drawing.
Make sure you get this picture. This picture is key. This picture will save you a lot of time. A lot of time. All right. So the preceding statement is called the empirical rule because the symmetric bell-shaped distributions, the given percentages are observed in practice. Furthermore, for the normal distribution, the empirical rule is a direct consequence of the very nature of the distribution. Notice that the empirical rule is a stronger statement than Chebyshev's theorem in that it gives a definite percentages, not just lower limits. Of course, the empirical rule applies only to the normal or the symmetric bell-shaped distributions, whereas Chebyshev's theorem applies to all distributions. All right. So there exist other distributions that we're not going to talk about in this class. Chebyshev's theorem applies to everybody, but for empirical rule, it only applies to the normal distribution. Okay. That's something important to know. Let's take a look at an example. And bear with me, this is one of those drawing examples. I'm gonna try my best. All right. Economic internet service has user connection speeds that are normally distributed with the mean of 28 megabytes per second and a standard deviation of 2.5 megabytes per second. All right. What is the probability that a connection selected at random takes from 28 to 30.5 megabytes per second? Okay. So easiest way to do a question like this, which is exactly how your homework would look, right? Draw the normal distribution. You have your x-axis, you have your bell shape. Maybe it looks like that, maybe it doesn't look like that, but you get the idea, right? In the middle is your mean mu. In this case, my mean is what? 28, right? And then all you have to do is just write out the other numbers, right? This is supposed to be mu plus sigma. So in this case, it's 28 plus 2.5, called as 30.5, right? And you could keep going out. Just keep adding another standard deviation to it. This is mu plus 2 sigma, right? So this one would be what? 32, 33.
32.
Not 32, 33, because it's 2.5.
Oh,
Yeah, 2.5 plus 30.5. This next one is mu plus 3 sigma. So just take the 33, add 2.5 to that. That's 35.5. On the left-hand side, right, this is mu minus sigma, right? So we're just taking a 28, subtracting 2.5 from that. What's that, 25.5, something like that? And then we have mu minus 2 sigma. So that's going to be minus 2.5. What's that? What's 5 minus 2? 3. So call that 23. Oh, yeah, that's the name of this class. I'm at 23. All right. Next, we got what? Mu minus 3 sigma, right? So then that one's going to be what? 21, 20.5, right? Now, this question asked me to go from 28 to 30.5. This is my answer right here. This is the area, all right? Now watch how simple this is. I drew the distribution, right? It's from mu to mu plus sigma. Let's go up to that picture. There it is, right? Between mu and mu plus sigma. How much is that? Right? You have mu and you have mu plus sigma. How much is that? What percentage is that? 34%. That's the answer. I'm done. All right. So the area right here, this is 34%. And how do I know that? Just go back up to the picture and just literally copy. Sorry. They gave you the bounds. We figured it out. We know that we want to go from, wrong pen. We want to go from mu to mu plus sigma. And we knew that that was this part right here, 34%. And that's it. So if this was web work, you'd be like 34 or 0.34, whatever, enter, and that's it.
You.
Sigma, not Q, sigma. It's some lowercase s in Greek. Mhm. So that's it. Homework's easy, right? And y'all know I like to show y'all what I was attempting to draw because I feel like I don't draw that well. This is why I never majored in art. But I am a hypocrite because I like to look at art. Y'all will really see me up in the Met just like, oh yeah, that this doesn't look like art, but oh yeah, this is the greatest thing I've ever seen. Ask me to draw it, I can't draw nothing. But this is what I was attempting to draw. This is what I was trying to do. All right. A little computer rendition of it. All right. So let's get into the sauce real quick before we leave, right? So what does a normal distribution tell us? If a continuous random variable has a normal distribution, then the area under the entire distribution is 1. The area over a specific interval of values from A to B is the probability that a randomly selected value falls between A and B. The distribution is symmetric and mound-shaped and is centered over the population mean mu. Most of the data, about 99.7% of the data, ranges from mu minus 3 sigma to mu plus 3 sigma. All right. And that's it. All right. So come sign the attendance. Have a happy spring break. Happy Easter. Happy yeah, yeah. We going on spring break after this. Yeah. Email me if you guys need anything, right? When we come back, see man. When we come back, we'll have our test. All right. I'm gonna send y'all out a update that's gonna list all the stuff. End on the 10th. It's a Friday. April? April. Yeah. Yeah. 13.
It's funny.
Yeah.
It's funny. I was coming here and I
Yeah.
was thinking like before I come to class, because I have